Welcome to another edition of Math for No Reason. In this edition, we will be examining how we can define sine of z if z is a complex number. Now we begin with the Euler identity, which says that e to the power ix is cos x plus I sin x. Now if you take the conjugate of this, so we get e to the power minus ix, and this is cos x minus I sin. Now if you add this 2, then we have e to the power ix plus e to the power minus ix is 2 cos x, and this gives us a definition of cos x as e to the power ix plus e to the power minus ix divided by 2. If instead of adding, if you subtract, then we get e to the power ix minus e to the power minus ix, and you see that then we have 2I sin x, and therefore we obtain sin x as e to the power ix minus e to the power minus ix by 2I. Now when we are trying to define sin z or cos z, we will be extending this notion. So we will define cos of z as e to the power iz plus e to the power minus iz divided by 2, and sin of z as e to the power iz minus e to the power minus iz by 2I. So in this way we have extended the definitions of sin x and cos x to the complex numbers. The next question would be that what properties of sin x and cos x are retained by these extended definitions to the complex numbers, that is sin z and cos z. And one of the most famous identity involving the cos and the sine is cos square x plus sin square x is equal to 1. So we will first check whether cos square z plus sin square z is still equal to 1 or not. So let's do that. Now cos square z plus sin square z is e to the power iz plus e to the power minus iz by 2 whole square plus e to the power iz minus e to the power minus iz by 2I whole square. Now using a plus b whole square and a minus b whole square, we can write the above as e to the power I 2z plus e to the power minus I 2z plus 2 into e to the power iz, e to the power minus iz cancels, so that gives us just 2 divided by 2 square, which is 4. And for the other also we get e to the power I 2z plus e to the power minus I 2z minus 2, and 2I whole square is 4I square, which is, so 1 by 4 is common, and because of the minus sign in the denominator, the first two terms cancel and we are only left with 4, so therefore we get 1. So cos square z plus sin square z continue to be equal to 1 even when we extend the definitions to complex numbers. However, another very important property of cos and sine when we are dealing with real numbers is that these are bounded functions. However, when we extend this to complex numbers, cos z and sin z are no longer bounded functions. Let us quickly see why. Now, let us take z is equal to n times I, where n is a natural number. Then cos of ni is e to the power I square n plus e to the power minus I square n divided by 2, which is e to the power minus n plus e to the power n by 1. We know that as n goes to infinity, e to the power n goes to infinity. So therefore, if you look at mod of cos ni, that goes to infinity as n goes to infinity. And since we have already seen that sine square z is 1 minus cos square z, so therefore both cos z and sine z are unbounded functions. So the boundedness property that we knew for the case of real x has to be given up as we extend the definition of sine and cos to the complex domain. It's a good point to stop. Thank you.